Getting started. Welcome to Physics 201. This is our first chapter. We're talking about mechanics, so we're going to talk first about measurement. So this involves talking about units, physical quantities, and vectors. For chapter 1, our main goals are solving physics problems. So we'll talk about the 4 steps you need to get started to solve a problem. We'll talk about 3 fundamental quantities that we talk about in physics, what we're starting with, and how to measure them with units. We're going to talk about significant figures and units and how to use them in calculations. We'll have a whole lab on significant figures and measurement. And we'll talk about vectors, which will probably be relatively long. We try to go over these because not everybody has had them before we started the class. So we'll first talk about adding and subtracting and what a vector means, and then we'll multiply them because multiplying a vector is not the same as regular multiplication. Okay, so the whole point of physics is to take information that we have and predict the future. But when we say we want to predict the future, what we do is we create a model. And a model is not, a tall person that wears beautiful clothing, but a model in this case is going to be something pared down. So we can take something like a dog running and we call it like a dot moving. Okay, so we're simplifying things so we can add math to them, because when you want to make an equation, you want to start with it as simple as possible, and then depending on what kind of answer you need, you can add complexity as needed. So a model is basically a virtual representation of a real thing, and you have all these little like toy moving parts that you can use in order to predict something that would happen in the real world. So here's a simple model that we could use answering a pretty simple question. Should you stand here? Okay, now that is a real world problem with a just sort of regularly asked question. But if you're building a model in physics, there's some other questions you should ask. Like, for instance, how far away is this person from the tree, right? How high up is this person cutting the tree? Right? We also would want to know which direction the tree is going to fall. And we also want to know how much precision we need around this target location. Because, for instance, by precision I mean orders of magnitude, right? Do we want to know within 10 feet how far or 10 meters how far this tree falls, right? If you know the tree could land anywhere from here to here and you're in that range, that matters a lot, right? So that would be sort of the accuracy of your measurement, and then the precision is how small it is. So here to here, that would also be bad. If you can figure out that the tree will land between here and here, that's good. So that's just the general ideas of what we need to know about measurement. And if we're measuring the tree, how good are our measurements? Because that's what tells us if we have something that looks like this or something that looks like this. So, turns out this person should not have stood here. Okay, so when we're solving physics problems, there's really 4 ways this is a general idea. All physics problems are sort of a puzzle that you solve slightly differently, but the key components are the same. There's no A, B, C to doing things. So the first thing is to identify. You read the problem and you figure out what concepts, variables, constants, and like parameters you need for solving this problem, and you make an estimate. And the reason you make an estimate, it sounds silly because you feel like you can just plug stuff in and get an answer, is to know if your answer makes sense at the end. We'll talk about that a little more later. Then the setup, you pretty much always want to draw a picture in physics. There's some exceptions to this, but since it's representing something in physical space usually, a picture really helps your brain to understand what's going on. It doesn't have to be magically artistic. It doesn't have to be beautiful. It just has to have the key elements and be practical. So the more simple it is, probably the better. But if you really enjoy drawing out like something cute and it helps you enjoy the class, go for it. The other thing is then you want to choose equations. So based on the variables and constants and things that you've identified from the problem, you want to choose equations. And also going back to number 1, when we talk about variables and constants, you're looking for key words that tell you this is a particular thing. Like if something says how far away, you can assume you're looking for a distance. It's not going to say what is the final position necessarily, but it might ask for it in more of a vernacular and in plain English words so that you can get the clue that you're supposed to do that. Okay, number 3 is where you actually do the math. So once you figure out all your numbers and variables and label everything and draw a picture, then you actually just start doing the math. So if you're just plugging in numbers right away, then you're probably jumping ahead to step 3 and it's easy to get confused. Last but not least, and very important, because I think some people try to just do this part, or maybe do a little bit of this and then this. Last but not least, you want to evaluate, which means you want to compare your answer to the estimate. So for instance, if your problem involves figuring out the speed of a car and you get like 900 miles per hour, then you probably did something wrong or the question is written very badly. So you want to have a prediction just so you know when you get an answer, it doesn't make any sense. That way you don't have to, if you don't have a way of looking up what your answer is or checking with a friend, you can at least decide, hey, maybe I made an algebra mistake, or maybe I wrote a number down wrong, or maybe I plugged something in my calculator wrong. All of those things happen all the time, and so having an idea of what your answer should look like can get rid of 90% of those kinds of mistakes.